Somewhere out there right now, a planet is moving through the darkness with no star to guide it. No sunrise has ever touched its surface. No warmth has ever reached its ground. It does not orbit anything. It does not belong to anything. It simply moves, carried by nothing but the momentum of a violent event that happened long ago, drifting through the space between stars like a ship that lost its harbor before it ever learned what a harbor was. We call it a rogue planet. And here is the part that should unsettle you. Astronomers now believe these wandering worlds may outnumber the stars themselves. For every star you can see in the night sky, there may be several planets out there with no star at all, untethered, unseen, and almost impossible to detect. Tonight, we are going to explore what happens to a planet when it loses its sun. We will examine how something so massive, so seemingly permanent, can simply be cast out into the void. We will ask what it would be like to stand on the surface of such a world, and why some scientists believe rogue planets might be more common in our galaxy than planets that still orbit something. By the end of this journey, you will understand why the discovery of rogue planets has quietly forced astronomers to reconsider what a normal planet even is, and why some of these drifting worlds might be carrying something that almost defies belief. To understand how a planet ends up utterly alone in the universe, we first need to understand how planets begin, because the story of a rogue planet is, in nearly every case, the story of a planet that was never meant to be alone. When most of us imagine a planet, we picture something like Earth, a world circling a star, warmed by daylight, governed by the rhythm of seasons. We picture Jupiter's storms swirling under sunlight, or Mars sitting quietly in the cold light of a distant sun. Every planet we have ever directly experienced, and nearly every planet we have ever directly observed, has had one defining feature in common: a star. That star provides light. It provides warmth. It provides the gravitational anchor that keeps a planet in a stable, predictable path. Without a star, there is no day. There is no night, because night never ends. There is no warmth, because nothing is providing any. For most of the history of astronomy, planets and stars were assumed to be inseparable. A planet, by definition, was something that orbited a star. That was simply what the word meant. But in recent decades, something strange began appearing in our data. Objects that had all the characteristics of planets: similar size, similar composition, similar formation, but that were not orbiting anything at all. They were simply out there, moving through interstellar space, untethered, unobserved by sunlight, detectable only because of the faint heat they still radiated from their own formation, or because of the gravitational fingerprint they occasionally left behind when their mass bent the light of a star passing far behind them. This was the first hint of something the textbooks had never accounted for. Planets that don't belong to anyone. A rogue planet, sometimes called a free-floating planet or an interstellar planet, is a planetary mass object that is not gravitationally bound to any star. It does not orbit a sun. It does not orbit anything at all, except perhaps, in rare cases, the gravitational center of an entire galaxy, the way stars themselves do. This single fact changes everything about what such a world experiences. A planet in a normal solar system follows a predictable path, year after year, century after century. Its temperature, while it might vary by season, falls within a relatively stable range because of consistent starlight. Its days and nights are governed by rotation, but rotation around a sun that provides at least some illumination. A rogue planet has none of this. Its temperature is dictated only by whatever heat remains from its own formation, and by the extremely faint warmth of the cosmic microwave background, the residual heat left over from the early universe itself. Its surface, if it has one, would likely be in permanent and absolute darkness, illuminated only by the distant pinpricks of starlight from stars it is not orbiting and will likely never approach. It is, in nearly every sense that matters to a planet, profoundly and permanently alone. For a planet to become rogue, something must happen to sever the gravitational bond it once had with its star, or in some cases, prevent that bond from forming in the first place. There are several pathways that lead to this outcome, and each one tells a different story about violence, chaos, or simple bad luck, written into the architecture of a planetary system. The most common pathway, according to current models, involves gravitational interactions between planets within a young solar system. When a solar system is first forming, it is rarely a calm, orderly place. Multiple planets may form in relatively close proximity to one another, all competing for stable orbits around the same star. In our own solar system, evidence suggests that the giant planets, Jupiter, Saturn, Uranus, and Neptune, underwent a long period of gravitational jostling early in their history, slowly migrating to their current positions. In many young systems, this jostling becomes far more extreme. A massive planet might pass close enough to a smaller one to fling it outward with tremendous gravitational force. Similar to how a slingshot launches a stone, if that gravitational kick is powerful enough, the smaller planet does not simply move to a wider orbit. It exceeds what astronomers call the escape velocity of the entire system. It leaves permanently. There is no slowing down. There is no eventual return. Once a planet has been ejected with sufficient velocity, it simply continues outward, carried by nothing but its own inertia, drifting farther and farther from the star system that created it, until that star system becomes nothing more than one indistinguishable point of light among billions of others. It is worth pausing here, because what we are describing is not a rare or exotic event. Current models of planetary formations suggest that ejections like this may be extremely common, perhaps even the rule rather than the exception. Many young planetary systems appear to form more planets than they can ultimately sustain in stable orbits. As the system settles over millions of years, gravitational competition sorts out which planets remain and which planets are cast out. This means that for every star system we observe today, with a handful of stable planets, there may have been other planets in that same system long ago that simply did not survive the process. They were not destroyed. They were not absorbed into the star. They were ejected, sent outward into the depths of the galaxy, never to return. If this model is correct, then our own solar system likely ejected planets of its own billions of years ago during the chaotic early period when Jupiter and Saturn were still settling into their orbits. Some scientists have speculated that an entire ice giant, similar in size to Neptune, may once have existed in our solar system and was flung outward long before recorded history could ever account for it. We will likely never find direct evidence of this lost planet. It would be somewhere out there now, indistinguishable from any other rogue world, carrying no marker of its origin, its history erased by time and distance. This is the first deeply unsettling truth about rogue planets. They are not anomalies. They may be the natural byproduct of how every solar system forms, Ejection is not the only path to becoming a rogue planet. There is a second, even stranger possibility. Some rogue planets may never have orbited a star at all. In regions of space where stars are actively forming, particularly within vast clouds of gas and dust known as stellar nurseries, astronomers have observed something unexpected. Alongside the formation of new stars, smaller clumps of gas occasionally collapse on their own, forming planetary mass objects directly, without ever coalescing into a true star and without ever settling into orbit around one. These objects form the same way stars do, through gravitational collapse within a cloud of gas. But they simply do not gather enough mass to ignite nuclear fusion in their core. They are too small to become stars, yet large enough to be considered planets in their own right. If this process is real, and observational evidence increasingly suggests that it is, then some rogue planets are not lost worlds that once had a sun. They are worlds that were born already alone. They never experienced a sunrise. They never had a sky lit by daylight, not even once, not for a single moment in their entire existence. There is something genuinely difficult to comprehend about this. Every world we know intimately, Earth, Mars, Venus, even the moons of distant gas giants, exists within a system governed by starlight. The idea of a planet-sized object forming, existing, and persisting for billions of years, without ever being illuminated by a sun, challenges something deeply intuitive about what a planet is supposed to be. This question brings us to one of the most genuinely startling results in modern astronomy. For years, astronomers assumed that rogue planets, if they existed at all, would be rare. After all, planets are difficult enough to detect when they orbit a star, reflecting that star's light or causing detectable wobbles in its position. A planet with no star at all would be far darker, far colder, and far harder to find. Yet, a series of observational surveys, particularly those using a technique called gravitational microlensing, began to suggest something remarkable. Gravitational microlensing works by observing what happens when a massive object, even a relatively small and dark one like a rogue planet, happens to pass directly between Earth and a distant background star. The gravity of the foreground object bends and magnifies the light of the star behind it, creating a brief, characteristic brightening that can be measured with precise instruments. This technique does not require the foreground object to emit any light of its own. It only requires gravity, and every object with mass has gravity. This makes microlensing one of the only ways to detect an object that produces no light whatsoever, drifting silently through the space between stars. Surveys using this method, conducted using telescopes, specifically designed to monitor millions of background stars for these brief lensing events, began detecting far more of these short, planet-scale lensing signatures than anyone had anticipated. The implications were significant enough that several research teams independently arrived at similar estimates. Some studies have suggested that free-floating, Jupiter-mass rogue planets could be nearly as numerous as the stars in our galaxy. Other research has gone even further, proposing that rogue planets of various sizes could outnumber stars by a ratio of several to one. If even the more conservative of these estimates is correct, it means our galaxy may contain hundreds of billions of rogue planets. If the more extreme estimates hold up under further investigation, that number could climb into the trillions. Think about what that actually means. The Milky Way contains, by most estimates, somewhere between 100 billion and 400 billion stars. If rogue planets exist in numbers comparable to or exceeding that figure, then for every star illuminating the galaxy, there could be one or more planet-sized worlds out there in total darkness, completely unaccounted for in our traditional understanding of what populates a galaxy. We have spent centuries cataloging stars, mapping constellations, building entire frameworks of astronomy around the light those stars produce. And it now appears that an enormous, perhaps even dominant, population of planetary bodies in our galaxy produces no light at all, and has been essentially invisible to us until very recently. This is not a minor footnote in astronomy. This may be one of the most significant revisions to our understanding of galactic structure in modern history, and most people have never even heard of it. Let's pause here and try to imagine, as honestly as we can, what existence on such a world would actually be like. Picture a planet roughly the size of Earth, perhaps slightly larger, drifting through interstellar space. There is no sun overhead, because there is no nearby star at all. The nearest star might be light years away, a faint point of light no brighter than any other star in a sky, otherwise dominated by absolute uninterrupted blackness. There would be no sunrise, there would be no sunset, there would be no concept of day, because the planet's rotation would change nothing about the amount of light reaching its surface. It would simply rotate through an endless, identical darkness, exposing different portions of its surface to the same featureless black sky, over and over, for as long as the planet continued to exist. If this world had once possessed an atmosphere, that atmosphere would likely have undergone a transformation almost impossible to imagine on Earth. Without the warmth of a star, atmospheric gases would gradually cool, depending on the planet's original temperature and atmospheric composition. Gases that we consider part of the air itself, nitrogen, oxygen, even the carbon dioxide that makes up much of Earth's atmosphere, could eventually cool below their freezing points. This means that on some rogue planets, the sky itself might fall. Snow made not of water, but of frozen nitrogen or frozen oxygen, could drift downward through a frigid, dark atmosphere, settling onto a surface locked in permanent night, building up layer after layer over millions of years. An entire ocean's worth of atmosphere, slowly transforming into solid ice and accumulating like snowfall on a world that never sees a winter end, because winter is the only season such a world has ever known or will ever know. This single image, an entire atmosphere frozen and fallen to the ground, is one of the strangest and most genuinely unsettling concepts in planetary science. It is not a hypothetical curiosity. It is the likely, perhaps inevitable, fate of any rogue world that once had an Earth-like atmosphere and was then cast into the emptiness between stars. Here is where the story becomes more complicated and considerably more interesting. Not every part of a rogue planet would necessarily be frozen solid. Surface temperature is only one part of the equation. Beneath the surface, a different story may be unfolding entirely. Planets generate internal heat through several processes that have nothing to do with sunlight. The decay of radioactive elements deep within a planet's core and mantle releases energy continuously over billions of years. This is the same process that keeps Earth's interior molten, drives plate tectonics, and powers volcanic activity. Even though Earth, of course, also benefits from the sun, a rogue planet would retain this same internal heat source. Radioactive decay does not care whether a planet orbits a star. It continues regardless, slowly warming the interior of any sufficiently large rocky or icy world from the inside out. This means that while the surface of a rogue planet might be locked in permanent, frozen darkness, hundreds of degrees below anything survivable, the deep interior of that same planet could, in principle, remain warm, possibly even warm enough, under the right conditions, to sustain liquid water. This single possibility has become one of the most quietly significant ideas in the search for life beyond Earth. And we will return to it because it raises a question that should genuinely change how we think about where life might exist in the universe. But to understand why this matters so profoundly, we first need to understand a particular category of rogue planet that has captured the imagination of astrobiologists more than any other. Some of the most intriguing rogue planet candidates are not rocky worlds like Earth, but rather worlds with thick, icy crusts, similar in composition to some of the moons we have already studied within our own solar system. Consider Europa, one of Jupiter's moons. Europa's surface is a frozen shell of ice, locked in temperatures far below anything survivable. Yet beneath that ice, scientists believe there exists a vast liquid ocean, kept warm not by sunlight, which barely reaches Europa at all given its distance from the sun, but by the immense gravitational stresses exerted on it by Jupiter itself. This gravitational flexing, called tidal heating, generates enough internal warmth to maintain liquid water beneath miles of ice. Now imagine a similar world, an icy planet with a deep subsurface ocean. Except this world is not orbiting a gas giant. It is not orbiting anything. It has been ejected into the emptiness of interstellar space. Without a nearby planet to generate tidal heating, this world would rely entirely on internal radioactive heat to keep its ocean from freezing solid. For a sufficiently large icy world, with enough radioactive material in its core, models suggest this could actually be possible. The surface would remain locked beneath an ice shell potentially many kilometers thick. But underneath that frozen exterior, an ocean could persist, dark, cold by Earth standards, but liquid for billions of years. This raises one of the more remarkable questions in modern astrobiology. Could there be life somewhere out there, existing entirely in the dark, beneath the ice of a planet with no sun at all? A planet that has never once been touched by starlight, yet might harbor an ocean that has remained liquid, stable, and potentially habitable for longer than Earth's own sun has existed. We do not know the answer. We may not know for a very long time, if ever, but the mere possibility forces us to reconsider one of the most fundamental assumptions in the search for extraterrestrial life. The assumption that habitability requires a star. For decades, the search for life beyond Earth has centered around a concept called the habitable zone, sometimes referred to more poetically as the Goldilocks zone. This is the region around a star where temperatures are neither too hot nor too cold for liquid water to exist on a planet's surface. It is a useful concept, and it has guided an enormous amount of productive scientific research. But it carries a built-in assumption that rogue planets quietly challenge. The assumption that a star is necessary for habitability at all, if internal heat alone, generated by radioactive decay and retained beneath an insulating layer of ice or rock, can maintain liquid water indefinitely, then habitability may not require a star's warmth at all. It may only require the right combination of internal composition, size, and insulation. conditions that a rogue planet could plausibly satisfy on its own, drifting silently through space, completely independent of any star. This idea has a name among astrobiologists. The concept of life that does not depend on photosynthesis or solar energy in any way, but instead draws all of its energy from geothermal or chemical processes deep within a planet itself. We already have a working example of something similar right here on Earth. Deep beneath the ocean's surface, far below where any sunlight penetrates, there exist hydrothermal vents, fissures in the seafloor where mineral-rich, superheated water flows up from below. Around these vents, entire ecosystems thrive, not through photosynthesis, but through a process called chemosynthesis, where microorganisms derive energy directly from chemical reactions involving substances like hydrogen sulfide, completely independent of sunlight. If life can exist this way on Earth, in an environment that never sees the sun, then in principle, similar life could exist within the subsurface ocean of a rogue planet, an ocean that has never once been touched by starlight in its entire existence, an ecosystem that has never known, and would never need to know, that stars exist at all. It is a genuinely profound thought. Life, evolving, surviving, perhaps even thriving, in complete and total isolation from every star in the universe, on a world utterly alone, in the vast darkness between galaxies of light it will never see. Given everything we have discussed so far, you might reasonably ask, if rogue planets emit no light and orbit nothing, how do astronomers find them at all? This challenge has driven some of the most creative observational techniques in modern astronomy. We have already discussed gravitational microlensing, which remains the most statistically productive method for estimating how many rogue planets exist across the galaxy as a whole. But microlensing events are brief, often lasting only hours or days, and they cannot easily be repeated or directly verified through follow-up observation, since the lensing object continues moving and will likely never again align so precisely with the same background star. A second method involves detecting the very faint heat that young rogue planets still radiate from their own formation. When a planetary mass object first forms, whether through ejection from a young solar system or through direct collapse within a stellar nursery, it retains a significant amount of residual heat from that formation process. This heat radiates primarily in infrared wavelengths, invisible to the human eye, but detectable by infrared telescopes specifically designed to find faint heat sources against the background cold of space. This is how some of the first directly imaged rogue planet candidates were identified, particularly within young star-forming regions, where free-floating, planetary mass objects were discovered drifting among newly formed stars, glowing faintly with the last residual warmth of their own creation. A warmth that, given enough time, billions of years, would eventually fade entirely, leaving the planet to cool toward the same frozen darkness as any other ancient rogue world. A third, more recent and increasingly powerful method involves space telescopes capable of directly observing extremely faint infrared sources across wide areas of sky. As detector technology has improved, astronomers have begun directly imaging an increasing number of rogue planet candidates, particularly the more massive examples that retain detectable heat signatures even after significant cooling. Each of these methods has its limitations. Microlensing tells us about overall population statistics, but rarely identifies a specific, well-characterized individual world. Infrared detection works well for young, still warm rogue planets, but becomes far less effective for ancient, cold worlds that have had billions of years to lose their residual heat. Direct imaging continues to improve but remains limited by the sheer faintness of these objects, which produce no light of their own and only the faintest infrared glow. This means that our current census of rogue planets is almost certainly a dramatic undercount. We are likely detecting only the youngest, warmest, and most massive examples, while an enormous population of older, smaller, colder rogue worlds remains essentially invisible to every technique we currently possess. In other words, the rogue planets we have found so far may represent only a small biased sample of a much larger, almost entirely undetected population drifting silently throughout our galaxy. Before we continue further into this journey, it is worth pausing on a single question that we will keep returning to throughout this documentary. If rogue planets truly do outnumber stars, and if some of them may harbor subsurface oceans capable of supporting life entirely independent of any star, what does that mean for how common life actually is in the universe? Our search for extraterrestrial life has, for most of its history, been built around searching for planets like Earth, orbiting stars like our Sun, within carefully calculated habitable zones. That search continues, and it remains valuable. But if an entire category of potentially habitable worlds exists that requires no star at all, worlds that may be more numerous than every starbound planet combined, then our search may have been looking in a comparatively narrow slice of where life could actually exist. We are not suggesting that rogue planets are teeming with life. We genuinely do not know. No subsurface ocean on a rogue planet has ever been directly observed, let alone tested for biological activity. This remains, for now, a possibility rather than a discovery, but it is a possibility substantial enough that serious astrobiologists take it seriously, substantial enough that it has begun appearing in scientific literature as a legitimate avenue worth further study, and substantial enough that it quietly reshapes one of the oldest questions in human history. Are we alone? If rogue planets are as common as current evidence suggests, then the universe may contain vastly more potentially habitable environments than we ever accounted for, hidden in total darkness, orbiting nothing, detectable only by the faintest bending of starlight, as they pass silently between us and a star they will never belong to. Let's now consider the long-term fate of these wandering worlds, because their story does not end the moment they are cast out into interstellar space. In many ways, that ejection is only the beginning of an entirely new chapter, one that unfolds over timescales that dwarf the entire history of human civilization. Once a planet has been ejected from its original system, or has formed without ever having a star at all, it continues moving through the galaxy, according to the same fundamental rules that govern every other object within it. It is still subject to the overall gravitational pull of the Milky Way as a whole, the same gravity that keeps our Sun and every other star in a slow, multi-hundred-million-year orbit around the galactic center. This means a rogue planet does not simply drift aimlessly forever in a perfectly straight line. Over sufficiently long timescales, it traces its own orbit around the center of the galaxy, just as stars do, just as our own solar system does. It becomes, in a sense, an extremely faint, extremely cold, planet-sized component of the galaxy's overall structure, following the same broad gravitational currents that shape the Milky Way's spiral arms. Occasionally, over the vast timescales involved, a rogue planet might pass relatively close to a star system, perhaps even close enough to be temporarily perturbed by that star's gravity. In exceptionally rare cases, models suggest a passing rogue planet could theoretically be captured into a new orbit around a star it encounters, effectively becoming a planet again after a period of complete isolation. This particular scenario remains almost entirely theoretical. Capturing a fast-moving rogue planet into a stable new orbit requires an extremely precise and unlikely combination of velocity, trajectory, and gravitational influence from the encountered star system. It is not impossible, but it appears to be vanishingly rare. For the vast majority of rogue planets, their fate is far simpler and considerably more lonely. They will likely continue drifting through interstellar space, completing their slow orbit around the galactic center. For the remainder of the galaxy's existence, they will outlive the stars that once might have been their neighbors. They will, in some cases, outlive entire star systems that form and eventually die around them, all while the rogue planet itself remains essentially unchanged, locked in its frozen, starless darkness. In a strange and almost poetic sense, rogue planets may be some of the most stable, long-lived objects in the entire galaxy. Stars eventually exhaust their nuclear fuel, expand, contract, and sometimes explode. Planetary systems are disrupted by stellar evolution, by gravitational instability, by the slow processes of cosmic time. A rogue planet, having already lost everything it could lose, gravitationally speaking, has remarkably little left to disrupt. It simply continues drifting, largely unchanged, for as long as the galaxy itself persists. This is one of the strange and quietly profound truths about these worlds. Having lost their star may, paradoxically, be the very thing that grants them an almost unimaginable degree of long-term stability. We have spent considerable time discussing the physical reality of rogue planets, their formation, their detection, their potential for harboring subsurface life. But there is another dimension to this topic worth sitting with for a moment, one that is less about physics and more about perspective. Human beings have never experienced true, total, permanent darkness on a planetary scale. Even our darkest nights are illuminated by starlight, by moonlight, by the faint glow of a sun that has simply rotated out of view temporarily, promising to return again within hours. A rogue planet experiences something we have no direct analog for. Not a long night, but an endless one. Not the absence of a single sun, but the absence of any meaningful starlight at all, beyond faint, distant points scattered across an otherwise featureless black sky. If, hypothetically, a human being could somehow stand on the icy surface of such a world, protected from the impossible cold and the absence of breathable atmosphere, what would they actually see above them? They would see stars, certainly, scattered points of light far in the distance, no different in appearance from the stars we see from Earth on a clear night. But there would be no moon, casting its reflected glow in a familiar, comforting rhythm of phases. There would be no zodiacal light, no soft band of scattered sunlight that traces the plane of any solar system, because there is no solar system to trace. There would simply be the same unchanging field of distant stars, frozen in place, never rising, never setting, because the absence of a nearby star means there is no meaningful concept of day to interrupt that view. And the planet's own rotation, while it would shift which stars are visible, would do so against an unchanging backdrop of permanent night. It is a genuinely difficult image to hold in your mind for very long, precisely because it is so fundamentally alien to everything human beings have ever experienced. We evolved on a world bathed in light and rhythm, day following night, season following season, all governed by our relationship with a single, reliable star. A rogue planet exists entirely outside that rhythm. It exists in a kind of cosmic stillness that human experience has no real reference point for. And yet, according to current scientific estimates, this kind of world, profoundly dark, profoundly cold, profoundly alone, may be one of the most common types of planet in the entire universe. That is not a small thought. It is the kind of thought that, once you have truly considered it, tends to change how you look at the night sky from that point forward. We began this documentary with a simple, unsettling premise: that planets can lose their stars, and that the universe may be filled with far more of these starless worlds than anyone previously imagined. We have explored how this happens through violent gravitational ejection during a solar system's chaotic youth, or through direct formation within a stellar nursery, never having had a star to begin with. We have explored what such a world might actually look like: an atmosphere potentially frozen and fallen to the ground, a surface locked in permanent night. And yet, beneath that frozen exterior, the genuine possibility of warmth, liquid water, and perhaps even life, sustained entirely by a planet's own internal heat. We have discussed how astronomers managed to find these nearly invisible worlds at all, through the subtle bending of starlight, through faint traces of residual heat, through increasingly sensitive infrared observation. And we have acknowledged that everything we have found so far likely represents only a small, biased fraction of a much larger population still hidden in the darkness between stars. But we have not yet addressed, perhaps the most important question of all, the question that takes everything we have discussed and turns it back toward ourselves. If rogue planets are truly this common, scattered throughout our galaxy in numbers that may rival or exceed the stars themselves, then how close might one actually be to our own solar system? Could one have passed near us before, completely undetected? Could one pass near us again? And if a rogue planet ever did pass close enough to our own solar system, what would actually happen? That question takes us into territory that is, quite genuinely, one of the more unsettling areas of modern planetary science, because the answer is not simply theoretical. There is reason to believe it may have already happened in our solar system's distant past, and there is no fundamental reason it could not happen again. To understand that risk, and to understand just how vulnerable a stable solar system actually is to an uninvited visitor passing through the darkness, we need to look closely at what gravitational chaos truly means, and why an object with no light of its own might be one of the most difficult dangers in the universe to see coming. That is where we will continue. But before we do, there is one more piece of this puzzle worth understanding properly. Just how many kinds of rogue planets actually exist, because not all wandering worlds are alike, and the differences between them turn out to matter enormously. It would be a mistake to imagine rogue planets as a single, uniform category of object. The term describes a fate, not a type. Any planet, regardless of size, composition, or original location within its system, can become rogue if the right gravitational circumstances align against it. This means the population of rogue planets drifting through our galaxy is likely just as diverse as the population of planets that remain safely in orbit around stars. Consider, first, the gas giants. Worlds similar in scale to Jupiter or Saturn are, according to current models, disproportionately likely to become rogue. This is partly a matter of simple physics. Gas giants are massive enough to exert powerful gravitational influence on other bodies within their system, which makes them more likely to be the ones doing the ejecting rather than the ones being ejected. But in densely packed young systems, where multiple giant planets form close together, it is entirely possible for one giant to be flung outward by another, similarly massive world. A rogue gas giant would retain much of its original structure, a thick atmosphere of hydrogen and helium, swirling cloud bands, perhaps even retained moons that were captured into orbit around the planet itself, before the entire system was cast loose together. In a strange way, a rogue gas giant with its own captured moons would represent a kind of miniature solar system in exile, a planet and its satellites, drifting together through the void, bound to each other, but to nothing else in the universe. Then there are the rogue terrestrial worlds, rocky planets similar in size and composition to Earth, Venus, or Mars. These worlds are generally considered less likely to be ejected, simply because they tend to be less massive and therefore exert less gravitational influence during the chaotic early period of system formation. But it does happen, and when it does, the result is one of the worlds we have already discussed in some detail. A once terrestrial planet, potentially once warmed by starlight, now drifting in permanent cold, its atmosphere, if it had one, slowly transforming into frost and snow across a surface that will never again see daylight. A third category deserves particular attention. The rogue ice worlds, sometimes referred to as failed planets or sub-brown dwarfs, depending on their exact size and formation history. These are the worlds we discussed earlier in the context of subsurface oceans, objects with thick icy shells that may conceal liquid water warmed entirely by internal radioactive heat. Current evidence suggests this category may be especially common among rogue planets, particularly those that formed directly within stellar nurseries rather than being ejected from an existing system. Finally, there exists a blurry, debated boundary between the largest rogue planets and the smallest possible stars, objects called brown dwarfs. Brown dwarfs are sometimes described as failed stars, objects that formed through the same gravitational collapse process as true stars, but never achieved sufficient mass to sustain full hydrogen fusion in their core. Some brown dwarfs do undergo a limited temporary form of fusion involving deuterium, a heavier isotope of hydrogen, which provides a brief period of warmth before fading. Others never fuse anything at all and simply cool slowly over billions of years, eventually becoming almost indistinguishable from a very massive rogue planet. This blurry boundary matters because it means some of the objects classified as rogue planets in early surveys may, on closer examination, actually be small brown dwarfs, and vice versa. Untangling this distinction has become an entire subfield of observational astronomy in its own right, requiring extremely precise measurements of mass, temperature, and chemical composition to determine which category a given drifting object truly belongs to. The size of a rogue planet does more than simply determine its classification. It fundamentally changes its long-term fate, its potential for retaining warmth, and even its potential for harboring life. A larger rogue planet retains heat for a much longer period of time than a smaller one. This follows from simple physics. A larger object has more volume relative to its surface area, meaning it loses heat to the surrounding void more slowly than a smaller object would. This is the same basic principle that explains why a large pot of soup stays warm longer than a small cup of tea, even if both started at the same temperature. For a rogue planet, this means a larger world, particularly a gas giant or a sub-brown dwarf, may continue radiating detectable infrared heat for hundreds of millions, or even billions, of years after its ejection. A smaller, Earth-sized rogue planet, by contrast, would likely cool to the background temperature of interstellar space, a few degrees above absolute zero, within a comparatively short astronomical time frame, perhaps tens of millions of years, though its deep interior could remain warm for vastly longer due to ongoing radioactive decay. This size-dependent cooling rate has direct consequences for our ability to detect these worlds. The rogue planets we have successfully identified through infrared observation tend to be skewed toward the larger, younger end of the population, simply because those are the ones still warm enough to glow detectably against the cold backdrop of space. Older, smaller rogue worlds, the ones that have had the most time to drift far from their point of origin, are almost certainly the most numerous and also the most invisible to our current observational techniques. In other words, our picture of the rogue planet population is not just incomplete, it is systematically biased toward exactly the type of world we are least likely to ever directly encounter, while remaining almost blind to the smaller, older, more numerous worlds that may make up the overwhelming majority of this hidden population. Some of the most direct evidence for free-floating planetary mass objects comes from observations of young star-forming regions, dense clouds of gas and dust, where hundreds or thousands of new stars are actively being born. Within these regions, astronomers using infrared telescopes have identified numerous objects with masses in the planetary range, drifting freely among the newly forming stars, not orbiting any of them, and apparently never having been gravitationally bound to any particular star at all. These young free-floating planets are still glowing with the heat of their own formation, making them comparatively easy to detect against the relatively young, still warm environment of the stellar nursery itself. These discoveries have been significant because they provide direct observational support for the idea that some rogue planets form independently through the same gravitational collapse process that creates stars and brown dwarfs, rather than only through later ejection from an established system. Without these observations, it might have been tempting to assume that all rogue planets originated as ejected members of ordinary solar systems. The presence of seemingly starless planetary objects within active star-forming regions tells a more complicated and arguably more interesting story. It suggests that the universe has at least two distinct manufacturing processes for rogue planets running simultaneously and continuously throughout the entire history of the galaxy. Some rogue planets are exiles, planets that once belonged somewhere and were violently removed. Others are orphans in a more literal sense, planetary mass objects that came into existence already alone, with no star to lose because they never had one in the first place. Both populations, exiles and orphans alike, end up in essentially the same final state, drifting alone through the galaxy, gravitationally independent and almost entirely invisible to traditional observation. But their origins remain meaningfully different, and understanding which formation pathway dominates the overall rogue planet population remains one of the open questions actively driving current research. It is worth taking a moment to consider the sheer scale of separation involved when we talk about rogue planets drifting through interstellar space. Within a typical solar system, distances between planets, while vast by everyday human standards, are still almost intimate when compared to the distances between entire star systems. The distance from the Sun to Neptune, the most distant major planet in our own solar system, is roughly 4.5 billion kilometers. Light, the fastest thing in the universe, takes about 4 hours to cross that distance. Now compare that to the distance between our Sun and the nearest other star system, Alpha Centauri, roughly 4 light-years away. That is over 20,000 times farther than the distance to Neptune. A rogue planet, once ejected from its original system, finds itself somewhere within this almost incomprehensibly vast gap between stars, a region of space so empty, so devoid of any other significant gravitational influence, that it may continue drifting, essentially undisturbed, for the remainder of the galaxy's history. This emptiness is, in its own way, part of what makes rogue planets so genuinely difficult to truly imagine. We are not talking about a planet that simply moved to a quieter neighborhood. We are talking about a planet that has been placed into one of the most profoundly empty environments that exists anywhere in the observable universe, an environment where the nearest significant object, a star, a planet, anything at all, might be measured not in millions of kilometers, but in trillions. And yet, despite this near-total isolation, current evidence suggests these worlds are not rare exceptions scattered sparsely across the galaxy. They appear to be a substantial, perhaps even dominant, component of the galaxy's total planetary population. The mathematics of loneliness, it turns out, may be one of the most common configurations for a planet to find itself in. It is genuinely remarkable how recently this entire picture has come into focus. As recently as the early 2000s, the existence of free-floating planetary mass objects was still considered a fringe possibility within mainstream astronomy, discussed primarily as a theoretical curiosity, rather than an established and significant population. The first credible candidates began appearing in published research in the mid-2000s, drawn primarily from observations of young star-forming regions. Over the following 2 decades, as both observational techniques and theoretical modeling improved dramatically, the picture shifted from these might exist to these almost certainly exist in large numbers to, more recently, these may represent one of the most numerous categories of planetary mass object in the entire galaxy. This is the kind of quiet, gradual revolution that rarely makes dramatic headlines, precisely because it did not happen through a single sudden discovery. It happened through years of accumulating evidence, survey after survey, each one adding incremental weight to a picture that grew more startling with every update. It is worth sitting with that for a moment. An entire, previously unrecognized population of planetary-scale objects, potentially as numerous as the stars themselves, has been quietly confirmed within the lifetime of many people currently alive today. We are, in a very real sense, among the first generations of human beings to even know that this hidden population of wandering worlds exists at all. There is a particular kind of difficulty involved in studying objects that are, by their very nature, designed by physics to remain hidden. Every other category of object astronomers study, stars, nebulae, galaxies, even black holes, announces its presence in some detectable way, whether through emitted light, through the light it blocks, or through the visible effects of its gravity on nearby, illuminated matter. A rogue planet, particularly an old, cold one, does almost none of this. It emits no significant light. It is generally too small and too distant from any other massive object to produce a detectable gravitational disturbance through normal observation. The only moments in which it reveals itself are fleeting, almost accidental, dependent entirely on chance alignment with a background star during a microlensing event, or on the rare circumstance of a young rogue planet still glowing faintly with residual formation heat. This means our entire understanding of the rogue planet population rests on a kind of statistical extrapolation. We detect a relatively small number of these brief chance alignments. We calculate, based on the rate at which we observe them and the areas of sky being monitored, how many such objects must exist throughout the galaxy to produce that observed rate. We are, in effect, counting raindrops by listening to occasional drips and using that limited information to estimate the size of an entire invisible ocean. This is not a criticism of the science. It is, in many ways, a remarkable achievement, extracting a meaningful population estimate for an entire class of object that produces almost no direct signal of its existence. But it does mean that every number we have discussed in this documentary so far, the estimate that rogue planets may rival or exceed the number of stars in the galaxy, should be understood as a current best estimate, refined repeatedly over the past 2 decades, and likely to be refined further as observational techniques continue to improve. It also means that the rogue planets we have actually detected and studied in any detail represent an extraordinarily small and almost certainly unrepresentative sample of the true population. We have glimpsed the edges of something vast, without yet being able to see the whole of it clearly. Perhaps the most quietly significant consequence of everything we have discussed is how it changes the way we might think about looking up at the stars. For most of human history, the night sky has represented a relatively complete inventory of what exists nearby in the universe. The visible stars, supplemented by planets we now know orbit them, formed the basis of essentially every model of the cosmos humans have ever constructed, from ancient star charts to modern stellar catalogues. We now understand that this view, however beautiful and however scientifically productive, is fundamentally incomplete. Scattered between every star you can see, and likely far closer to our own solar system than any of those distant points of light, there may exist dark, planet-sized worlds, utterly invisible, utterly silent, drifting through the same patch of sky you are looking at, without producing so much as a single photon of light for you to notice. The galaxy, it turns out, is not simply a collection of bright points scattered across darkness. It may be better understood as an almost continuous field of planetary mass objects, the vast majority of them dark and starless, with the bright, easily visible stars representing only the illuminated minority within a far larger, far quieter population. This reframing does not diminish the wonder of the night sky. If anything, it deepens it. Every time you look upward, you are seeing only a fraction of what is actually out there. The visible universe of stars is, in a very real sense, only the brightest layer of a much deeper, much stranger structure, most of which remains, and may always remain, entirely hidden from direct view. Everything we have explored so far, the formation of rogue planets, their staggering estimated numbers, the strange physics of their frozen, starless surfaces, and the genuine possibility of hidden oceans and hidden life beneath their ice, builds toward a single, more urgent question that we have only briefly touched on. If these worlds are genuinely this common, drifting silently throughout the galaxy in numbers that may exceed every star combined, then the assumption that our own solar system exists in permanent, guaranteed isolation from this hidden population deserves serious scrutiny. We have treated rogue planets so far as distant curiosities, fascinating objects to study from a comfortable distance. But distance, in a galaxy where these worlds may number in the hundreds of billions, is not a permanent guarantee. It is at best a current circumstance, one shaped entirely by chance, by the particular arrangement of objects within our corner of the Milky Way at this particular moment in cosmic time. What would actually happen if one of these dark, massive, gravitationally significant wanderers passed close enough to our solar system to matter, not in some distant abstract sense, but in a way that could measurably disturb the orbits of planets we depend on, including our own? If rogue planets truly exist in numbers that may rival or exceed the stars themselves, scattered throughout the galaxy in near total darkness, then what happens if one of them does not stay distant? What happens if one drifts close enough to actually matter? To answer that, we need to understand something about the architecture of our own solar system that most people never think about. Not the planets themselves, which we know well, but the much larger, much quieter region surrounding them, a region that extends far beyond Neptune, far beyond Pluto, into a zone where the sun's gravitational grip becomes thin enough that almost anything passing through it could leave a mark. Most discussions of the solar system end at Neptune, or perhaps stretch slightly further to include Pluto and the icy bodies of the Kuiper Belt. But the sun's gravitational influence extends vastly further than this, out to a region known as the Oort cloud, a vast, roughly spherical shell of icy debris, believed to surround the solar system at distances measured not in millions, but in trillions of kilometers. The Oort cloud is not a place we have ever directly observed in detail. Its existence is inferred primarily from the behavior of long-period comets, icy objects that occasionally fall inward toward the sun from extraordinarily distant, extraordinarily slow orbits so vast that a single trip around the sun can take thousands, or even millions, of years to complete. These comets are believed to originate from the Oort cloud, nudged out of their extremely distant, extremely stable orbits by some external gravitational disturbance, and falling inward toward the inner solar system, after spending most of their existence in a region so far from the sun that its light would appear as nothing more than a slightly brighter star. This is the key detail that matters for our discussion. The outer edge of the Oort cloud is not gravitationally locked in place. It exists at the very limit of the sun's influence, in a region where the gravitational pull from the rest of the galaxy, including any passing star, brown dwarf, or rogue planet, can become comparable to, or even exceed, the gravitational pull from our own sun. This means the outer solar system is, in a very real sense, vulnerable. Not to collision, which remains exceptionally unlikely given the vast distances involved, but to gravitational disturbance. An object passing through or near the Oort cloud does not need to strike anything directly. It only needs to pass close enough, with enough mass, to subtly alter the delicate gravitational balance that keeps these icy bodies in their long, slow, stable orbits. It is worth being precise about what we mean when we say a passing object could disturb the outer solar system, because the word disturbance can sound abstract until you understand the actual mechanism involved. Every object in the Oort cloud exists in a delicate gravitational balance, held in its slow, distant orbit by the combined pull of the Sun and the relatively faint, distant influence of the rest of the galaxy. This balance is stable over long periods of time, but it is not rigid. It can be altered by the introduction of a new, sufficiently massive gravitational source passing nearby. If a rogue planet, particularly one with the mass of a gas giant, were to pass through or near the outer reaches of the Oort cloud, its gravity would interact with the icy bodies in that region exactly as gravity always does, pulling on them, however slightly, and altering their existing orbits. For some of these icy bodies, the effect might be negligible, a barely perceptible nudge that changes their orbit by an amount too small to ever notice on any human timescale. For others, particularly those that happen to pass relatively close to the intruding object's own path, the effect could be considerably more dramatic. Their orbits could be stretched, bent, or in some cases, redirected entirely, sending what was once a slow, distant resident of the outer solar system on a new trajectory, potentially one that falls inward, toward the inner solar system, toward the planets, toward us. This is the mechanism behind what scientists call comet showers, periods, during which the rate of long-period comets entering the inner solar system increases significantly above its normal background level. While comet showers can be triggered by several different causes, the passage of a massive object, whether a passing star or a sufficiently large rogue planet, through the outer solar system is considered one of the most plausible mechanisms. Here is where the conversation moves from theoretical mechanism to genuine scientific debate, because there is reason to believe this kind of disturbance may not be a purely hypothetical future risk. It may already be part of our solar system's actual history. Paleontological and geological records on Earth show a long and well-documented history of mass extinction events, periods during which a significant percentage of all species on the planet died out within a relatively short geological time frame. Some of these extinctions have well-established causes, such as the asteroid impact, widely understood to have contributed to the extinction of the dinosaurs roughly 66 million years ago. But not every extinction event in Earth's history has such a clear, single, well-documented cause. Some researchers, examining the broader pattern of extinction events across hundreds of millions of years of Earth's history, have noted what appears to be a statistical periodicity, a tendency for major extinction events, or at least elevated rates of asteroid and comet impacts, to cluster around intervals of roughly 26 to 30 million years. This observed periodicity has led to a long-running, genuinely contested hypothesis within astronomy that something out there, some periodic gravitational disturbance, might be responsible for triggering these clustered impact events. By periodically destabilizing the outer solar system and sending a burst of comets falling inward toward Earth. It is important to be precise about the scientific status of this idea. It remains a hypothesis, not an established fact. The statistical evidence for periodicity in the extinction record has been debated extensively within the scientific community, with some researchers finding the pattern statistically significant and others arguing that the apparent periodicity may be an artifact of incomplete or unevenly sampled geological data. This is not a settled question, and any documentary claiming otherwise would be overstating the current scientific consensus. But the hypothesis itself, regardless of whether it ultimately proves correct, has produced one of the more fascinating chapters in the search for hidden objects within and beyond our solar system, because it gave rise to a serious, decades-long scientific search for a specific kind of object, a hypothetical companion to our own sun. In the 1980s, several astronomers and physicists, working from the observed periodicity in the extinction record, proposed that our sun might not be entirely alone. They hypothesized the existence of a distant, faint companion object, sometimes referred to informally as Nemesis, orbiting the sun at an extraordinarily wide distance, far beyond even the outer reaches of the Oort cloud, on an orbit so long that it would take tens of millions of years to complete a single pass. According to this hypothesis, this companion object, whether a faint red dwarf star or a brown dwarf too dim to have been noticed in previous surveys, would periodically pass close enough to the Oort cloud during its long orbit to gravitationally disturb it, triggering comet showers and elevated impact rates here on Earth at roughly the same intervals suggested by the extinction record. This hypothesis prompted genuine, dedicated astronomical searches, using both ground-based telescopes and, eventually, dedicated infrared space surveys, specifically designed to detect faint, cool objects exactly like the one being proposed. These surveys were thorough enough that over time, they substantially ruled out the existence of any companion star bright enough or close enough to match the original hypothesis. Before moving further into the rogue planet hypothesis specifically, it is worth acknowledging that gravitational disturbance of the Oort cloud does not necessarily require any passing object, star, brown dwarf, or rogue planet to arrive from outside our solar system at all. There is a second, entirely separate mechanism, capable of producing similar effects. One rooted not in any visiting object, but in the structure of the galaxy itself. As our solar system orbits the center of the Milky Way, a journey that takes roughly 230 million years to complete a single full circuit, it does not travel through a uniform, empty galactic environment. The galaxy's overall gravitational field, shaped by the combined mass of hundreds of billions of stars, vast clouds of gas and dust, and the as yet poorly understood substance known as dark matter, varies depending on exactly where within the galaxy our solar system happens to be located at any given time. This variation produces what astronomers call the galactic tide, a gentle but persistent gravitational stretching effect exerted on our solar system by the broader structure of the galaxy as a whole. While considerably weaker than the more localized effect of a nearby passing object, the galactic tide acts continuously, and its strength varies as our solar system moves through different regions of the galaxy, particularly as it periodically passes through the denser plane of the galactic disk during its long orbital journey, an event that occurs roughly every 30 million years or so a periodicity that some researchers have also connected to the same disputed pattern observed in Earth's extinction record. This means that, when considering what might be capable of periodically destabilizing the outer Oort cloud and triggering elevated comet activity here on Earth, astronomers must actually consider at least two distinct independent mechanisms operating simultaneously. The rare, localized effect of a passing star, brown dwarf, or rogue planet, and the more regular, but generally weaker, effect of our solar system's own periodic motion through the varying gravitational structure of the galaxy itself. Untangling which of these mechanisms, if either, is actually responsible for the disputed periodicity in the extinction record remains an active and genuinely unresolved area of research. It is entirely possible that both mechanisms contribute, acting together at different times throughout our solar system's long history, occasionally reinforcing one another's effects and occasionally acting in relative isolation. This added complexity is part of why the broader question remains scientifically contested, rather than definitively resolved, and it is a useful reminder that the rogue planet hypothesis we have been exploring throughout this documentary represents one serious candidate explanation among a small number of plausible competing mechanisms rather than the only possible explanation for the patterns observed in Earth's deep geological past. The Nemesis hypothesis, in its original form, is generally considered unsupported by current observational evidence. No companion star of the proposed brightness and distance has ever been found, despite searches sensitive enough that such an object, if it existed within the proposed parameters, likely would have been detected by now. But here is where the story becomes directly relevant to everything we have discussed about rogue planets. Because ruling out a companion star does not rule out a companion planet, or more precisely, it does not rule out the existence of an entirely unrelated, unbound rogue planet or brown dwarf that might, at some point in the deep past or distant future, simply pass through our solar system's outer reaches by sheer chance, with no need for it to be gravitationally bound to our Sun at all. The Nemesis hypothesis specifically required a companion object permanently bound to the Sun in a very long, very wide orbit. The rogue planet hypothesis requires nothing of the sort. It only requires that, given how common these wandering worlds may actually be throughout the galaxy, one of them might simply happen to pass close enough to our solar system, completely independent of any binary relationship with our Sun, purely as a matter of statistical chance over sufficiently long timescales. This distinction matters enormously because it means that even with the original Nemesis hypothesis substantially discredited, the broader question of whether a rogue planet could disturb our solar system's outer reaches remains entirely open and arguably more scientifically grounded than the companion star hypothesis ever was. Precisely because rogue planets are now understood to be vastly more numerous than once believed. This raises a natural and important question. Given how vast interstellar distances actually are, how close would a rogue planet actually need to pass to our solar system in order to produce a meaningful gravitational effect? The answer depends heavily on the mass of the passing object and the precise distance of its closest approach. But current models suggest that an object with the mass of a large planet or a small brown dwarf could begin to produce a measurable gravitational disturbance to the outer Oort cloud at distances of roughly 1 to 2 light years and potentially produce a significant disturbance, capable of meaningfully increasing the rate of comets falling toward the inner solar system at distances closer than 1 light year. To put this in perspective, the nearest known star system to our own, Alpha Centauri, sits at a distance of roughly 4.2 light years. This means that an object passing at half that distance, or even closer, while still representing an enormous distance by any everyday human standard, would actually be passing through a region of space considerably closer to our solar system than our nearest known stellar neighbor. Given the staggering estimated population of rogue planets within the galaxy, and given that these objects move independently through interstellar space over timescales of millions and billions of years, the statistical likelihood that one has passed within this kind of disturbing range of our solar system at some point during its 4.5 billion year history is not negligible. Several independent lines of research modeling the expected frequency of close stellar and substellar passages based on current rogue planet population estimates suggest that disturbing passages, while still rare on any human timescale, may occur on average once every several million years, a frequency that aligns at least loosely with the disputed periodicity observed in the extinction record. Though again, this connection remains a hypothesis rather than an established conclusion. Perhaps the most genuinely unsettling aspect of this entire scenario is not the disturbance itself, but the fact that we would likely have very little advance warning before it began. Recall everything we discussed in the first part of this documentary about how difficult rogue planets are to detect. They emit no light of their own. Older, smaller examples emit only the faintest residual infrared heat, a heat signature that becomes progressively harder to detect the further away the object is, and the colder it has become over time. A rogue planet approaching our solar system from interstellar distances, even one massive enough to eventually disturb the Oort cloud, would likely remain essentially undetectable using current observational techniques, until it was already relatively close, certainly within a few light years, and potentially much closer than that, depending on the object's specific size, temperature, and composition. This is fundamentally different from the kind of warning we might receive for other cosmic hazards. A star approaching our solar system would be visible, its light detectable across vast distances long before it became close enough to matter, allowing decades or centuries of advance notice as astronomers tracked its slow approach. A rogue planet, dark and cold, offers no such courtesy. It could, in principle, already be relatively close, several light years away, well within the range that current models suggest could eventually become disturbing to the outer solar system, and we would have no current means of detecting it unless it happened to pass directly in front of a background star during exactly the right moment for a microlensing event to be observed. This is not intended as an alarmist claim that such an object is currently approaching us. There is, as of now, no known candidate object on a trajectory that threatens our solar system, but the broader point stands on its own. Independent of any specific current threat, our ability to detect an approaching rogue planet lags significantly behind the timescale we would need for any kind of meaningful preparation, simply because the physics of detecting a dark, cold object across interstellar distances remains genuinely difficult, even with our most advanced current instruments, to appreciate just how different the rogue planet detection problem is. From the dangers we already actively monitor, it helps to look briefly at how we currently track the more familiar category of cosmic hazard: near-Earth asteroids and comets that already orbit within or close to our own solar system. Over the past several decades, dedicated astronomical survey programs have systematically scanned the skies for these objects, gradually building an increasingly complete catalogue of asteroids large enough to pose a meaningful risk if they were ever to strike Earth. These programs work by repeatedly imaging the same regions of sky over time, identifying objects that move relative to the fixed background of distant stars, and then calculating their orbits with enough precision to determine, often decades in advance, whether any of them will ever pass uncomfortably close to our planet. This approach works remarkably well for near-Earth asteroids, precisely because these objects, while dark, are still close enough and still illuminated by enough direct sunlight to be detectable through reflected light. Using the same basic observational principle that has guided astronomy since Galileo first turned a telescope toward the heavens. The closer an object is to the sun, the more sunlight it reflects, and the easier it becomes to detect even a relatively small dark object against the surrounding blackness of space. A rogue planet breaks this entire detection model. It is not close to any sun. It reflects essentially no light, because there is no significant nearby light source for it to reflect in the first place. The very method that has allowed us to build increasingly confident, increasingly complete catalogues of near-Earth asteroids simply does not apply to an object drifting through the much darker, much emptier space between entire star systems. This is why, despite decades of genuinely impressive progress in planetary defense against asteroids and comets, our capability to detect an approaching rogue planet remains, by comparison, still in its earliest stages, dependent almost entirely on the much rarer, much less predictable phenomenon of gravitational microlensing, a technique that can tell us a great deal about the rogue planet population as a whole, but very little about any specific object's exact current position or trajectory relative to our own solar system. This gap between our two detection capabilities, mature and effective for nearby asteroids, still nascent and limited for distant rogue planets, represents one of the genuine remaining frontiers in planetary defense, and one that will likely require entirely new observational strategies rather than simply scaled-up versions of our current asteroid tracking infrastructure to meaningfully close. Let's now walk through, carefully and with appropriate scientific caution, what the realistic consequences of a disturbing rogue planet passage would actually look like, separating the genuinely concerning possibilities from the kind of exaggerated science fiction scenarios that occasionally circulate in less careful discussions of this topic. The first and most important point to establish is what would not happen: a rogue planet passing at the kind of distance we have been discussing. Even a close passage by astronomical standards, measured in light years rather than light minutes, would not result in any direct collision with Earth or with any planet in our solar system. The distances involved remain far too vast for any kind of direct physical encounter. This is not the scenario being described, despite how dramatic some popular discussions of rogue planets occasionally make it sound. What would actually happen, in the most scientifically grounded version of this scenario, unfolds over a much longer and more gradual timescale, and involves several distinct stages. In the initial stage, the passing rogue planet would gravitationally disturb the outer Oort cloud, altering the orbits of some icy bodies within it. Some of these disturbed comets would be sent on new trajectories that bring them, over a period of thousands of years, slowly falling inward toward the inner solar system, the journey from the Oort cloud to Earth's orbital region, taking, in many cases, well over 1,000 years to complete, given the enormous distances involved. This means that, even in a scenario where a rogue planet did pass close enough to meaningfully disturb the Oort cloud, the resulting increase in comet activity reaching the inner solar system would not be immediate. It would unfold gradually, over centuries or millennia, as progressively more of the disturbed comets complete their long inward journey. This is, in a strange way, a kind of cosmic slow-motion consequence, a disturbance set in motion that would not fully manifest for generations, possibly for far longer than that. In the following stage, astronomers on Earth, assuming our civilization persists and maintains its observational capabilities, would likely notice the increased rate of long-period comets entering the inner solar system well before any of them posed a direct threat to Earth itself, simply because modern comet detection and tracking has become remarkably capable. Long-period comets, once they enter the inner solar system, are typically detected years, sometimes more than a decade, before reaching the orbital region near Earth, providing meaningful warning time, even if the comet were ultimately found to be on a potentially dangerous trajectory. This is a genuinely important point of scientific reassurance amid an otherwise unsettling topic. The danger posed by a hypothetical comet shower triggered by a passing rogue planet is not a sudden, unannounced catastrophe. It would unfold as a gradually elevated background rate of risk, spread out over an extended period of time, with each individual comet remaining subject to our existing detection and tracking capabilities, long before it could pose any direct threat. None of this means the scenario carries no genuine concern. It simply means the concern is statistical and cumulative, rather than sudden and catastrophic. If a rogue planet passage genuinely elevated the rate of long-period comets entering the inner solar system over a period of several thousand years, even a modest increase in that rate, sustained over such a long time frame, would meaningfully increase the cumulative probability that at least one of those comets eventually crosses Earth's orbital path. At the same time, Earth happens to occupy that point in its orbit. Most of these comets would simply pass through the inner solar system without ever coming close to any planet. But across thousands of comets, over thousands of years, the statistical odds of an eventual close encounter, while still individually small for any single comet, accumulate into something that becomes scientifically meaningful when considered across the full duration of an elevated comet shower period. This is the real, scientifically grounded version of the risk that a passing rogue planet represents. Not a sudden, planet-destroying impact arriving with no warning, but a long-term, statistically elevated background risk unfolding gradually across a timescale far longer than any single human lifetime, potentially longer than the entire span of recorded human civilization. It is also worth noting that this entire chain of events depends on a specific, relatively close passage by a sufficiently massive rogue planet, an event that current models suggest is rare on any human timescale, even if it may occur with enough regularity to show up as a periodic signal across the much longer span of Earth's geological history. It is worth pausing here to note that, while no rogue planet has ever been directly detected passing through our solar system, we have, in recent years, directly observed something closely related: small interstellar objects passing through our solar system from outside it entirely, confirming that material from beyond our own sun's gravitational influence does, in fact, occasionally arrive here. The first such object, an elongated, unusual body discovered in 2017, was confirmed to have originated from outside our solar system entirely, arriving on a trajectory that proved it was never gravitationally bound to our sun and was simply passing through on its way back out into interstellar space, never to return. A second confirmed interstellar visitor, this one identifiably a comet given its visible tail of outgassing material, was detected 2 years later, providing further direct confirmation that our solar system is not the sealed, isolated environment it might intuitively seem to be, but is instead regularly, if rarely, visited by material originating from entirely different star systems. These two confirmed objects were both relatively small, certainly nowhere near planetary scale, but their discovery carries significant implications for the broader rogue planet discussion. If small, dim interstellar objects are passing through our solar system with enough frequency that we have already detected, two of them using only the relatively limited survey capability available over the past decade, then the basic physical process they represent, material from outside our solar system occasionally passing through it, is clearly a real and ongoing phenomenon, not a purely theoretical possibility. This does not mean a rogue planet is likely to pass through our solar system anytime soon. The vast difference in size and detectability between a small interstellar asteroid and a planetary mass rogue world means these two categories of object behave very differently in terms of how easily and how often we are likely to notice them. But the confirmed detection of interstellar visitors, however small, provides a kind of real-world proof of concept for the broader idea that our solar system exists within a galaxy through which material regularly moves, undeterred by any boundary we might have once imagined separating our space from everyone else's. It also raises an intriguing question for future observation. If our current survey capabilities, still relatively limited compared to what is being planned for the coming decade, were able to detect two small interstellar objects passing through, what might more advanced, more sensitive future surveys eventually reveal? Some astronomers have suggested that significantly more capable next-generation survey telescopes, specifically designed to scan large areas of sky, repeatedly and rapidly, may begin detecting interstellar objects on a much more regular basis, potentially including, eventually, planetary mass objects passing through the outer reaches of our solar system, if any happen to do so, within the survey's operational lifetime. In other words, the title of this documentary speaks of a terrifying truth, and there is genuine substance to that framing. But the substance lies not in an imminent, specific threat, but in the broader realization that our solar system exists within a galaxy populated by an enormous number of dark, massive, gravitationally significant objects, any one of which could, over sufficiently long timescales, meaningfully alter the architecture of our own cosmic neighborhood, largely without warning, and largely without our current ability to detect it coming until it is already relatively close. To make this scenario feel less abstract, it may help to walk through a single, clearly hypothetical timeline of what such an event might actually look like in practice, while being explicit that this is an illustrative exercise grounded in current scientific understanding, not a prediction of any specific event. Imagine, first, a rogue planet with roughly the mass of Jupiter, drifting through interstellar space on a trajectory that happens to bring it within half a light year of our Sun, a distance still vastly larger than anything within our solar system's planetary region, but close enough, according to current modeling, to begin meaningfully perturbing the outer Oort cloud. In the years immediately surrounding this passage, the object itself would likely remain extremely difficult to detect using current technology, given its distance and its lack of any significant light emission. It is entirely plausible that such a passage could occur without being directly observed at all, its presence inferred only afterward, through its gravitational aftermath, rather than through any direct observation during the encounter itself. Over the following several centuries, the gravitational disturbance to the Oort cloud would begin to manifest as a gradually increasing rate of long-period comets being nudged onto new trajectories, some falling inward toward the Sun. Given that the journey from the outer Oort cloud to the inner solar system can take well over 1,000 years for many of these objects, this would not represent a sudden flood, but rather a slow, gradually building increase, unfolding across many human generations, several hundred to perhaps 1,000 years after the initial gravitational disturbance. Astronomers, assuming continued observational capability, would likely begin noticing a statistically elevated rate of new long-period comets entering the inner solar system, distinguishable from the normal background rate through careful long-term record keeping. Modern comet detection and orbit tracking systems, already remarkably capable, would identify each of these comets years in advance of any potential close approach to Earth, providing ample opportunity for assessment and, if necessary, response. Across the following several thousand years, the elevated comet rate would gradually return to its normal background level as the disturbed population of icy bodies either falls inward and is consumed, is ejected entirely from the solar system through further gravitational interactions, or gradually settles back into a new, stable configuration within the outer solar system. The entire episode, from initial gravitational disturbance to the eventual return to baseline conditions, would likely unfold across a timescale of several thousand years, far longer than any single human lifetime. Longer even than the entire span of recorded human civilization to date. This is, perhaps, the single most important detail to hold on to when considering this scenario honestly. It is not a single dramatic event, but an extended, multi-generational process, one that any sufficiently advanced and persistent civilization would have ample opportunity to observe, understand, and respond to as it unfolds, rather than experiencing it as a sudden, unannounced catastrophe. There is something worth acknowledging here that goes beyond the purely statistical framing of risk we have just walked through, something closer to a philosophical unease than a scientific concern, and it is worth sitting with honestly. rather than rushing past it. For most of human history, we have understood the solar system as a relatively closed, relatively stable system. The planets orbit the Sun in predictable paths. The occasional comet or asteroid passes through, but the overall architecture, the basic arrangement of our cosmic neighborhood, has felt fundamentally fixed, a stage upon which the drama of human civilization unfolds without much concern for the scenery itself changing. What the rogue planet population teaches us is that this sense of fixed stability is, in a deeper sense, an illusion created by the relatively short timescale of human observation. Across the vastly longer timescale of the solar system's actual history, 4.5 billion years, our cosmic neighborhood has likely been disturbed, reshaped, and influenced by passing objects more times than we can currently account for. Simply because we have only been capable of observing the sky carefully for a few hundred years, a duration so brief on a cosmic timescale that it is statistically unlikely to have included anything but the quietest possible period in our solar system's long history. We are not living through an unusually dangerous moment in our solar system's existence. We are most likely living through an unusually quiet one, a calm interval between disturbances that have already happened in the deep past and will likely happen again in the deep future, on a timescale so much longer than human civilization that it is almost impossible to feel any genuine, visceral concern about it, even while understanding intellectually that the underlying physics is entirely real. This is, in its own way, one of the more profound perspective shifts available within this entire subject. The solar system is not a static, protected sanctuary. It is a dynamic system, embedded within a much larger, much more chaotic galaxy, constantly subject to forces and objects beyond its own boundaries, most of which remain invisible to us, simply because we have not yet developed the means to see them clearly. Given everything we have discussed, it is worth asking directly: are we doing anything about this? Is there any meaningful effort underway to improve our ability to detect an approaching rogue planet before it becomes a genuine concern? The honest answer is that current planetary defense efforts are overwhelmingly focused on a different, more immediate category of risk: near-Earth asteroids and comets already within or relatively close to our own solar system. Objects considerably easier to detect than a dark, distant rogue planet still light years away. Programs specifically designed to catalog and track these nearer objects have made substantial progress over the past few decades, significantly improving our ability to detect potentially hazardous asteroids years or even decades before any possible close approach. Detecting a distant interstellar rogue planet, however, remains a fundamentally different and considerably more difficult challenge. Such an object would not be orbiting anything detectable through normal means. It would not reflect significant sunlight, given its distance from any star. It would only reveal itself through the kind of rare, fleeting gravitational microlensing events we discussed at length in the first part of this documentary. Events that, by their very nature, cannot be predicted or anticipated for any specific object in advance. We can only observe them as they happen, essentially by chance, scattered unpredictably across the sky. This means that, realistically, our advance warning capability for a genuinely close rogue planet passage remains limited, certainly compared to the kind of advance warning we have developed for nearer asteroid and comet threats. future advances in infrared survey capability, including increasingly sensitive space-based telescopes designed to detect extremely faint heat signatures, may eventually improve this situation, allowing astronomers to detect approaching dark objects at greater distances and with greater lead time. But as of now, a rogue planet approaching from interstellar distances would likely remain undetected until it had already drawn relatively close, in astronomical terms, to our solar system. It would be incomplete to discuss our current detection limitations without acknowledging the genuine progress being made to address them, because this is an active and rapidly evolving area of astronomy, not a static problem that has simply been left unaddressed. Several major astronomical facilities, either recently operational or scheduled to begin operation within the coming years, are specifically designed with capabilities that bear directly on the rogue planet detection problem. Wide-field survey telescopes capable of repeatedly imaging enormous areas of sky, monitoring millions of background stars simultaneously for the brief brightening characteristic of a microlensing event, represent one of the most promising approaches, since the statistical power of microlensing surveys scales directly with the number of stars being continuously monitored. The more stars under observation at any given time, the more frequently a chance alignment with a passing dark object, whether nearby or distant, will be captured. Space-based infrared observatories, operating above the distorting and obscuring effects of Earth's own atmosphere, also continue to improve our ability to detect the faint residual heat still radiated by younger rogue planets, particularly within nearby star-forming regions where free-floating planetary mass objects have already been identified in growing numbers. As these instruments become more sensitive, and as the data they collect is analyzed using increasingly sophisticated computational techniques, the population of confirmed and candidate rogue planets is likely to continue expanding substantially over the coming decade, refining our understanding of exactly how common these worlds actually are, and potentially identifying examples considerably closer to our own solar system than anything currently known. There is also a growing scientific interest in directly searching for evidence of any rogue planet within a few light years of our own sun specifically, motivated in part by the broader questions about Oort cloud stability and historical comet shower periodicity that we discussed earlier in this documentary. While no such nearby candidate has been confirmed, the increasing sensitivity of ongoing and planned surveys means that if such an object does exist within a relatively close range, the coming years and decades represent perhaps the best opportunity humanity has ever had to actually find it. This is worth holding on to as a closing thought on the detection question. We are not simply waiting passively for a rogue planet to announce itself through some dramatic future disturbance. Astronomers are actively working right now, using some of the most sophisticated observational tools ever built, to extend our ability to see into exactly the kind of darkness these objects inhabit. The gap between what we can currently detect and what may actually be out there is real, but it is also gradually and deliberately being narrowed. It is worth pausing on something easy to overlook in all of this. The very terminology used to describe these objects has shifted considerably as our understanding of them has matured, and that shifting vocabulary tells its own quiet story about how scientific consensus actually develops. In the earliest research discussing the possibility of planetary mass objects unbound to any star, scientists used a range of inconsistent and sometimes informal terms, including free-floating planets, sub-brown dwarfs, planetary mass objects, and interstellar planets, often within the same body of research, reflecting genuine uncertainty about how to classify objects that did not fit comfortably into either the established category of planet, which traditionally implied orbiting a star, or the established category of star, which implied sustained nuclear fusion. The term rogue planet, the phrase most commonly used in popular science communication today, including in the title of this very documentary, emerged somewhat later, gaining traction, particularly as the population estimates, derived from microlensing surveys, began suggesting these objects were far more common than the more clinical, technical terminology had initially implied. The word rogue itself carries a deliberate connotation, evoking a sense of wandering, of having broken away from an expected, orderly path, which captures something genuinely true about the physical history of many of these objects, even if it leans toward a more dramatic framing than the strictly technical literature typically employs. This linguistic evolution reflects a broader pattern common throughout the history of astronomy. A new category of object is first described using cautious, provisional, often inconsistent terminology, before a more settled and widely adopted vocabulary eventually emerges, usually only after enough observational evidence has accumulated to give the scientific community genuine confidence that the category in question represents something real, distinct, and worth a name of its own. The fact that rogue planet has now become the dominant, broadly accepted term, used not only in popular documentaries like this one, but increasingly within serious astronomical literature itself, is itself a quiet signal of just how thoroughly the existence of this population has moved from speculative possibility to established scientific fact over the past 2 decades. It is also worth noting that the formal classification boundary between a rogue planet and a brown dwarf, the failed star category we discussed earlier, remains genuinely contested within the scientific community, with different research groups sometimes applying different mass thresholds to distinguish between the two categories. This is not merely a semantic disagreement. It reflects a deeper, still unresolved question about whether these two categories of object actually represent fundamentally different formation processes. Planets, formed through the gradual accumulation of solid material within a protoplanetary disk, versus brown dwarfs formed through the direct gravitational collapse of a gas cloud, or whether they instead represent a single continuous spectrum of objects that simply happen to span a wide range of masses with no genuinely sharp dividing line between the largest possible planet and the smallest possible failed star. This remains one of the more interesting open questions in the broader study of planetary and substellar objects, and it is a useful reminder that even the basic act of classifying these wandering worlds, deciding what to call them, and where exactly the boundaries of that category should be drawn, remains an active, evolving area of scientific discussion, rather than a settled matter of simple definition. This is not a reason for alarm about any specific, currently known threat, because no such threat has been identified. It is instead a sober acknowledgement of a genuine gap in our current observational capability, one that exists not because of any lack of scientific effort, but because of the fundamental physical difficulty of detecting an object that, by its very nature, was never designed by the universe to be easily seen. So far, we have focused primarily on the danger a rogue planet might pose to our own solar system from a distance, through gravitational disturbance of the outer Oort cloud. But there is another, somewhat different category of danger worth exploring. One that shifts our perspective from our solar system as the potential victim to a hypothetical scenario in which we, or some future version of humanity, might actually encounter a rogue planet directly. This scenario moves further into speculative territory than anything we have discussed so far. But it remains grounded in real physics, and it raises questions worth considering carefully, both about the practical challenges involved and about what such an encounter might actually reveal. Imagine, for a moment, a future era of human spaceflight, advanced enough that journeys beyond our own solar system have become genuinely achievable, whether through extremely long-duration crewed missions, sophisticated robotic probes, or some propulsion technology not yet developed. In such a future, the discovery of a nearby rogue planet, one of the countless dark worlds we now understand to be scattered throughout the galaxy, could represent one of the most significant exploration targets imaginable. Unlike a planet orbiting a distant star, a rogue planet drifting through interstellar space would not require an immense journey across the punishing gravity well and radiation environment of an active star system to reach. If a sufficiently close rogue planet were ever identified within a few light years of our own solar system, it would, in principle, represent one of the more directly approachable interstellar destinations available to any future human exploration effort, precisely because it exists in the relatively empty, relatively unobstructed space between stars, requiring no complex orbital insertion around an active, energetic sun. If such an exploration mission were ever to succeed, what might it actually find? Drawing on everything we have discussed throughout this documentary, the most scientifically interesting possibility remains the question of subsurface oceans and the chemistry, or potentially biology, that might exist within them. A robotic probe capable of penetrating the icy crust of a sufficiently large rogue planet, perhaps using techniques similar to those currently being developed for exploring the subsurface oceans of icy moons within our own solar system, could potentially sample an environment that has remained completely isolated from any external stellar influence for billions of years. This isolation is scientifically significant in its own right, independent of whether life is ultimately found. A subsurface ocean on a rogue planet would represent one of the most chemically and thermally stable long-term environments theoretically available anywhere in the universe, protected from the disruptive radiation, the gravitational chaos, and the eventual stellar evolution that affects every planet still orbiting an active star. If complex chemistry, or even primitive biological processes, can develop and persist within such an environment, it would tell us something profound about the actual requirements for life's emergence, potentially suggesting that the presence of a star, long considered an essential ingredient in the search for habitability, may be far less important than previously believed. There is also the more straightforward scientific value of studying a rogue planet's geology and composition directly, providing a kind of natural laboratory for understanding how planets evolve over extremely long time scales in the complete absence of stellar influence. Everything we currently know about long-term planetary evolution has been derived from studying planets that have spent their entire existence under the influence of a star. A rogue planet offers something genuinely unique. A natural experiment in planetary evolution running in the opposite condition, in total isolation, for potentially billions of years. There is a particular variation on the rogue planet scenario that deserves its own dedicated attention, because it may represent one of the more genuinely promising candidates for harboring life among all the possibilities we have discussed so far. A rogue gas giant that was ejected from its original system while still retaining its full system of moons. We touched briefly on this possibility earlier, but it is worth exploring more deeply here, because the physics involved produces a genuinely distinct and arguably more favorable environment for potential habitability than a simple rogue terrestrial planet would offer on its own. Within our own solar system, several of the large moons orbiting Jupiter and Saturn are kept warm, at least in part, through a process called tidal heating, in which the immense gravitational pull of the much larger planet repeatedly flexes and stresses the moon's interior as it travels along its orbit, particularly when that orbit is not perfectly circular. This continuous flexing generates internal heat through friction, in much the same way that repeatedly bending a piece of metal back and forth generates heat at the bend point. This is the mechanism widely believed to be responsible for maintaining the subsurface liquid ocean beneath Europa's icy crust, and similar tidal heating is thought to drive the dramatic geysers observed erupting from the icy surface of Saturn's moon, Enceladus. Critically, this tidal heating mechanism has nothing to do with the Sun whatsoever. It depends entirely on the gravitational relationship between a moon and the much larger planet it orbits. This means that if an entire gas giant system, the planet and its full complement of orbiting moons, were ejected together from their original star system, becoming a single gravitationally bound unit drifting through interstellar space, the tidal heating relationship between the planet and its moons would continue completely undisturbed by the loss of their original star. In other words, a moon like Europa, if it somehow found itself ejected along with Jupiter into the depths of interstellar space, would likely continue generating internal heat through tidal flexing in essentially the same way it does now, completely independent of whether Jupiter itself still orbited the Sun or was instead drifting alone through the darkness between stars. This matters enormously for the broader habitability discussion, because it means an exiled gas giant system could potentially host not just one, but several tidally heated moons, each with its own subsurface ocean, each maintained not by fragile internal radioactive decay alone, but by the much more robust and long-lasting mechanism of gravitational tidal flexing between planet and moon, a relationship that, once established, could persist essentially unchanged for as long as the orbital architecture of the system itself remains stable. A rogue gas giant system considered this way begins to look less like a single, isolated, frozen world and more like an entire miniature solar system in exile, complete with its own internal heat budget, its own potentially habitable subsurface environments, and its own long-term orbital stability, none of which requires the presence of any star whatsoever. If life can exist within Europa's ocean today, sustained by tidal heating rather than sunlight. There is no obvious physical reason why a similar ocean, on a similarly tidally heated moon, could not continue supporting life indefinitely. Even after that, Moon's home planet has been cast into the absolute darkness of interstellar space. This particular scenario, an exiled gas giant carrying its own retinue of potentially habitable moons, may represent one of the more genuinely compelling and physically well-grounded possibilities for life existing entirely independent of any star, anywhere in the galaxy. It would be dishonest to discuss this exploration scenario without acknowledging just how far beyond our current technological capability such a mission remains. Even the nearest plausible rogue planet candidate, should one ever be confirmed, within a few light years of our solar system, would still require a journey across distances that dwarf anything human spacecraft have ever attempted. Our fastest current spacecraft, traveling at speeds that took decades to achieve even the relatively modest distances within our own solar system, would require many thousands of years to cross even a single light year. Using current propulsion technology, closing this gap would require fundamental advances in propulsion technology, whether through nuclear-based propulsion systems, currently in early theoretical and experimental development, through extremely large-scale laser-driven sail concepts capable of accelerating small probes to a meaningful fraction of the speed of light, or through some other propulsion approach not yet developed. Even under highly optimistic assumptions about future technological progress, a crewed or robotic mission specifically targeting a confirmed nearby rogue planet likely remains, at minimum, many decades away from genuine feasibility, and potentially much further than that. This means that, for the foreseeable future, our understanding of rogue planets will continue to rely almost entirely on indirect observation, microlensing surveys, infrared detection, and increasingly sophisticated theoretical modeling, rather than any kind of direct exploration. The dark worlds we have spent this documentary exploring will likely remain, for at least the coming decades, objects we can only study from an enormous distance, inferred from faint statistical signals, rather than directly observed and explored. There is something worth pausing on here, a kind of quiet tension between how significant rogue planets appear to be, in terms of their sheer numbers and their potential scientific importance, and how genuinely inaccessible they remain to direct human investigation. We have spent this entire documentary establishing that rogue planets may be among the most numerous planetary bodies in the entire galaxy, potentially harboring some of the most stable, long-lived environments theoretically capable of supporting life. And yet, despite this apparent significance, they remain almost entirely beyond our practical reach, hidden not only by their physical darkness, but by the sheer, almost incomprehensible distances separating even the nearest of them from our own solar system. This combination, profound potential significance, paired with profound practical inaccessibility, is not unique to rogue planets within astronomy. It echoes a pattern we see throughout the broader search for understanding our place in the universe. Many of the most important unanswered questions in astronomy, the nature of dark matter, the ultimate fate of black holes, the question of whether life exists elsewhere, share this same quality. We can reason about them, model them, even detect indirect evidence of them, while remaining genuinely unable to reach out and examine them directly. Perhaps this is simply an honest reflection of where humanity currently stands in its relationship with the broader universe. We have developed remarkable tools for inferring the existence and properties of objects and phenomena far beyond our direct physical reach. But the gap between knowing that something exists and actually being able to study it up close remains, for now, one of the defining limitations of our current era of cosmic exploration. Let's return now to perhaps the most significant open question raised throughout this entire documentary. The question of whether rogue planets might actually harbor life, because it deserves a more careful, more complete treatment than we have given it so far. We have established the basic physical case for why this remains a genuine scientific possibility. Sufficiently large, icy rogue planets could maintain subsurface oceans, kept liquid by internal radioactive heat rather than starlight, for timescales potentially exceeding the current age of the universe. We have also noted that life on Earth has already demonstrated the ability to thrive in environments that never receive sunlight, drawing energy instead from chemical processes around deep-sea hydrothermal vents. But it is worth being precise about exactly how far this reasoning can responsibly be taken, because there is an important difference between establishing that something is physically possible and establishing that it is likely, or that it has actually happened. The chemosynthetic ecosystems found around Earth's hydrothermal vents did not arise independently of the rest of Earth's biosphere. They exist within a planet that also has a sunlit surface, an oxygen-rich atmosphere produced by billions of years of photosynthetic life, and a long, complex evolutionary history connecting deep-sea organisms to the broader tree of life that also includes surface-dwelling, sunlight-dependent organisms. It remains a genuinely open scientific question whether life could originate entirely independently from the very beginning in a deep, dark, subsurface ocean with absolutely no connection to any sunlit environment at all, the way it would have to on a true rogue planet that has never had a star. Current scientific understanding of how life first originated on Earth itself remains incomplete, with several competing hypotheses about whether the earliest life arose in shallow, sunlit pools in deep-sea hydrothermal environments, or through some other pathway entirely. Until this question is better resolved, even for our own planet's well-studied history, it remains difficult to make confident predictions about whether a similar process could occur within the completely isolated subsurface ocean of a rogue planet that has never had any external energy source beyond its own internal heat. This is precisely the kind of distinction the more careful corners of astrobiology insist on maintaining. Rogue planet oceans represent a genuinely interesting, scientifically serious hypothesis about where life might exist, not a confirmed or even strongly favored prediction. The honest scientific position remains that we do not currently know whether life could originate and persist in such an environment, only that the basic physical conditions required for liquid water to exist there appear to be plausible, based on our current understanding of internal planetary heating. There is something valuable in sitting with this uncertainty honestly, rather than resolving it prematurely in either direction. If it turns out that life requires sunlight, or at least some external energy source beyond a planet's own internal heat, in order to originate in the first place, even if it can later adapt to survive without it, as appears to be the case with Earth's deep-sea ecosystems. Then rogue planets, however numerous, however potentially habitable in terms of liquid water alone, might ultimately prove to be sterile worlds, possessing all the physical ingredients for life, except the specific spark required to actually begin it. If, on the other hand, it turns out that internal heat alone, combined with the right chemical ingredients, can be sufficient to originate life, independent of any external stellar energy whatsoever, then the implications become genuinely staggering. Given how numerous rogue planets appear to be throughout our galaxy, and by extension throughout the broader universe, this would suggest that potentially habitable environments for life's origin may be far more common than the star-centered model of habitability has traditionally assumed, scattered not only around stars within their narrow habitable zones, but throughout the vast, dark spaces between every star in every galaxy, on every sufficiently large icy world drifting through that darkness. We do not currently know which of these possibilities is correct. This uncertainty is not a failure of the science. It is, instead, an honest reflection of how genuinely difficult this particular question is, and how much we still have left to learn about the actual requirements for life's emergence, even using the only confirmed example of life we currently have access to study, our own. There is one further implication worth exploring before we bring this documentary to a close, because it connects the specific subject of rogue planets to one of the broadest and most enduring questions in all of astronomy. Why, if the universe is as vast and as old as we understand it to be, have we found no confirmed evidence of life anywhere beyond Earth? This question, often referred to as the Fermi paradox, has produced decades of serious scientific speculation, ranging from the possibility that intelligent civilizations are simply extraordinarily rare, to the possibility that they tend to destroy themselves before achieving the technological capability for interstellar communication, to the possibility that they exist but remain undetectable using our current methods of searching. Rogue planets introduce a genuinely novel consideration into this long-running discussion. If life can, in fact, originate and persist within the subsurface oceans of starless worlds, sustained entirely by internal heat, rather than any external stellar energy, then such life would face an entirely different set of circumstances than life that develops on a sunlit planetary surface. Life confined entirely beneath a thick shell of ice, on a planet with no star, would have no direct path toward developing astronomy, no ability to observe the night sky, no reason to ever develop the conceptual framework of stars, distance, or an external universe at all, since every aspect of its environment would consist entirely of dark water and ice, with absolutely no view of anything beyond it. Such life, even if it became remarkably complex, even if it somehow developed intelligence comparable to or exceeding our own, would face a fundamentally different relationship with the broader universe than we do. It would have no obvious incentive or pathway toward developing radio communication, space travel, or any of the technologies we typically associate with detectable, communicative civilizations, simply because it would have no direct evidence that an external universe beyond its own ocean even exists. This raises a genuinely interesting possibility within the broader Fermi paradox discussion, that life, even reasonably common and reasonably complex life, might be heavily concentrated within environments fundamentally incapable of ever announcing their own existence to the rest of the universe. Not because such life is hiding deliberately, but because the physical circumstances of its environment never provide it with any reason or any means to look outward in the first place. If this is even partially correct, it suggests a humbling possibility that the universe could be considerably more populated with life than our current search methods, which depend heavily on detecting radio signals, atmospheric biosignatures, or other forms of outward-facing technological or biological activity, would ever be capable of revealing. Life confined within the dark, sealed ocean of a rogue planet would remain permanently invisible to virtually every search technique we currently employ, not due to any limitation in our technology, but due to the fundamental nature of the environment in which that life exists. This does not resolve the Fermi paradox. It does not tell us whether life actually exists on any rogue planet anywhere in the galaxy, but it does add a genuinely thought-provoking dimension to the broader question of why we have not yet found confirmed evidence of life beyond Earth, suggesting that our search may be systematically biased toward finding only the kind of life capable of, and interested in, looking outward while remaining permanently blind to an entirely different category of life that may exist in considerable abundance. Sealed away in silence, beneath the ice of worlds with no star to ever draw their attention upward. Before bringing this documentary to its close, it is worth directly addressing something that often surrounds this particular topic in popular discussion: the tendency for rogue planets to be portrayed in less careful corners of the internet and occasionally in fictional media as imminent doomsday objects hurtling toward Earth on a collision course, often associated with vague and scientifically unfounded predictions of a specific looming arrival date. None of what we have discussed throughout this documentary supports that kind of framing, and it is worth being explicit about why. There is no credible scientific evidence for any rogue planet currently on a collision course with Earth, or even on a trajectory that would bring it close enough to disturb our solar system within any meaningful human timescale. The genuine scientific discussion surrounding rogue planets concerns their overall population across the galaxy, the statistical likelihood of disturbing passages occurring over time scales of millions of years, and the fascinating, carefully qualified possibility of subsurface habitability, none of which translates into any specific identifiable near-term threat to Earth. This distinction matters because it reflects a broader and important principle in how legitimate science communication should handle genuinely uncertain, genuinely fascinating topics. It is entirely possible and indeed necessary to communicate real scientific uncertainty. The fact that rogue planets are difficult to detect, that we cannot rule out a disturbing passage having occurred in the deep past, that we cannot perfectly predict the timing of a future passage, without sliding into the kind of unfounded, specific doomsday claims that occasionally attach themselves to genuinely interesting scientific subjects. The honest scientific position is considerably more nuanced and arguably more interesting than either dismissive reassurance or sensational alarm. Rogue planets represent a real, measurable, and statistically significant feature of our galaxy's structure, with real implications for the long-term history and future of our solar system, evaluated over timescales of millions of years, rather than the kind of short-term, specific predictions that tend to circulate in less careful corners of public discussion. This documentary has aimed throughout to hold that careful, honest middle ground, taking the underlying science seriously enough to explore its genuinely unsettling implications, while remaining disciplined about distinguishing established findings, plausible hypotheses still under active scientific debate, and clearly speculative possibilities that remain interesting, precisely because they have not yet been confirmed or ruled out. As we approach the end of this exploration, it is worth stepping back from the specific mechanics of gravitational disturbance, comet showers, subsurface oceans, and theoretical exploration missions, and considering what this entire subject ultimately reveals about our broader understanding of the universe. We began this documentary with the image of a single planet, drifting alone through absolute darkness, carried by nothing but the momentum of whatever violent event first separated it from its star, or born already alone, with no star to lose in the first place. We have since learned that this image, however strange and however isolated it might initially seem, may actually describe one of the most common types of planet in the entire galaxy, potentially outnumbering every star-bound planet, every visible point of light in the night sky combined. This is, in itself, a genuinely significant revision to how we should think about the structure of our galaxy, and by extension, the structure of the broader universe. For most of human history, our mental image of the cosmos has been built almost entirely around visible light, around the bright points of stars and the planets we have managed to detect orbiting them. We are only now beginning to understand that this visible structure may represent a comparatively small, brightly illuminated minority within a far larger, far darker, far quieter population of wandering worlds. The terrifying truth referenced in this documentary's title is, in the end, not a single dramatic threat poised to strike without warning. It is something quieter and in some ways more profound. The realization that the universe contains vastly more than what we can currently see, that the comforting visible order of stars and planets represents only the illuminated surface of a much deeper, much darker structure, and that our own solar system, however stable it has appeared, throughout the brief span of recorded human history, exists within a galaxy populated by an almost incomprehensible number of dark, massive, gravitationally significant objects, any one of which could, given enough time, meaningfully reshape the quiet stability we have always taken for granted. It is worth closing the observational portion of this documentary with a simple, grounding question. If we did manage to point a sufficiently powerful telescope directly at a confirmed, nearby rogue planet, what would we actually see? The honest answer, for the vast majority of these worlds, is disappointingly little, at least in terms of anything resembling the dramatic, richly detailed planetary imagery that space telescopes have produced for worlds within our own solar system. A rogue planet, lacking any nearby star to illuminate it, would appear, even through the most advanced direct imaging instruments currently available or currently planned, as nothing more than an extremely faint point of infrared light, its only detectable signal the residual heat still leaking outward from its interior, with absolutely no surface detail, no visible atmospheric bands, no discernible features of any kind. This stands in stark contrast to the iconic images we have of planets like Jupiter or Saturn, with their richly colored cloud bands and visible storm systems all of which are made possible specifically because those planets are illuminated by direct sunlight, reflecting that light back toward our telescopes in a way that reveals genuine surface and atmospheric structure. A rogue planet offers no equivalent opportunity. Whatever clouds, storms, or surface features it might possess would remain entirely invisible to any telescope relying on reflected light, simply because there is no significant light for it to reflect. The only information we could realistically extract from direct observation of most rogue planets would come from analyzing the faint infrared spectrum of their own self-generated heat, a technique that can reveal a surprising amount of information despite the lack of visual detail. By carefully measuring exactly which infrared wavelengths a rogue planet emits most strongly, and how that emission changes over time as the object rotates, astronomers can infer its approximate temperature, estimate its size, and in some cases, even detect the chemical signatures of specific compounds present in its atmosphere or on its surface, including, in the most exciting potential cases, signatures associated with water ice, frozen nitrogen, or other materials relevant to the subsurface ocean hypothesis we have discussed throughout this documentary. This means that, even though we will likely never have a genuine, detailed photograph of a rogue planet's surface in the way we now have for Mars or Jupiter, we are not entirely without meaningful observational tools. Infrared spectroscopy, the technique of breaking down an object's faint heat signature into its component wavelengths, represents one of the most promising avenues for extracting genuine scientific understanding from these otherwise visually unremarkable, profoundly dark worlds, allowing us to learn a surprising amount about their composition and physical state, even while their actual surface remains, and will likely long remain, something we can only imagine rather than directly see. We do not know exactly how many rogue planets exist within our galaxy. Only that current evidence suggests the number is large, possibly comparable to or exceeding the number of stars themselves. We do not know whether any of these dark worlds harbor life within their hidden, sunless oceans. Only that the basic physical conditions required for such life appear to be plausible, given what we currently understand about internal planetary heating. We do not know whether a rogue planet has passed close enough to our own solar system in the deep past to trigger any of the extinction events recorded in Earth's geological history, only that the underlying mechanism remains scientifically plausible, and that the broader population of rogue planets makes such an encounter over sufficiently long timescales a statistical possibility worth taking seriously. And we do not know whether such an encounter might happen again, at some point in the deep future. Only that nothing in our current understanding of physics or galactic structure rules it out, and that our current ability to detect such an approaching object remains limited by the fundamental difficulty of finding something that, by its very nature, produces almost no light for us to see. This is, in many ways, the appropriate place to leave this particular journey. Not with a tidy resolution, but with a clearer, more accurate understanding of just how much remains genuinely unknown, and just how much larger, stranger, and darker our own galaxy may actually be than the comfortable, starlit picture most of us carry in our minds when we look up at the night sky. The next time you find yourself outside on a clear night, looking up at the scattered points of starlight overhead, it may be worth remembering everything this documentary has explored. Every star you can see represents a single illuminated point within a galaxy that may contain hundreds of billions of additional planetary bodies, producing no visible light at all, drifting silently through the same field of view, utterly indifferent to whether anyone happens to be looking in their direction. Somewhere among that hidden dark majority, there may exist worlds with subsurface oceans that have remained liquid, stable and undisturbed for longer than human civilization has existed. Oceans that have never once been touched by light from any star, and that may or may not contain the patient, slow beginnings of life, unlike anything we have ever encountered. We cannot see these worlds directly. We can only infer their existence through the faintest, most fleeting signatures. A brief brightening of a distant star's light as an invisible mass passes silently in front of it, gone again within hours, never to repeat in exactly the same way. It is a strange kind of astronomy, studying a population of objects almost entirely through the absence of evidence they leave behind, rather than through any direct signal they choose to send. And yet, through that faint, indirect evidence, we have learned something genuinely profound about the structure of our own galaxy, something that would have seemed like pure speculation only a few decades ago, and that now stands as one of the more quietly significant revisions to our understanding of what actually populates the space between the stars. The universe, it turns out, is not simply a collection of bright lights scattered across darkness. It is a vast, mostly dark structure, within which the bright lights represent only the visible minority. Somewhere within that darkness, drifting silently, alone, and largely unseen, an unknown number of worlds continue their slow journey through the galaxy, carrying whatever history, whatever chemistry, and perhaps whatever life they have managed to develop in complete and total isolation from every star in the observable universe. That is the terrifying truth and the genuine wonder of the rogue planets drifting through space.